Hi, mechanisms and modes of mass transfer. This is a lecture recorded for BE 3500 at Cornell University, and it's simply because I am away for this lecture, so we're recording only for that purpose. Um, so let's see. What are the prerequisites for this module? Now, if we are going to talk about mass transfer, we need to know how much mass is there. So what is concentration? We have to define it properly. And various units of concentration. We also have to really know what is equilibrium, meaning, when things are over, after a long time, when it's together, one would be diffusing into the other, let's say, and what would be my final concentration, because that's the direction that the system would be driving toward. And then the gradient of a function is very basic because, as you saw in heat transfer, the rate of heat flux, rate of heat flow or heat flux is proportional to the gradient of temperature. So it's the gradient that is driving this kind of a transport process, which is just the slope. Okay, so how does this chapter relate to the others? So we are here on chapter 10 and we finished chapter 9. So chapter 9 simply defined those concentrations, and we said how non-equilibrium leads to mass transfer, which is exactly like in heat transfer, that if you have a temperature difference between two things that are in contact, then heat will flow from hot to cold. So that's all we did. So chapter 9 is like chapter 1 in heat transfer, and chapter 10 is like chapter 2 in heat transfer. So here we're going to talk about mechanisms and modes of mass transfer. And so why do we even bother with this chapter? So the thing is, for design purposes, for engineering, for practical use, we need to know how fast a process is going. So let's say in this diffusion process, so this is the same animation that I showed you for heat transfer, where these circles, the red circles, were at a higher temperature, let's say. But here, they're all at the same temperature, and the reds are identical to the blues, except I have colored them. And I want to see how the reds diffuse into the blue. So in this case, we're talking about diffusion of the red into the blue. As you can see, it takes time, and that is critical for doing something real. So how fast does it does the diffusion process go? How long does it take to reach close to equilibrium? And same here, this kind of diffusion process, what you see on this side, the it's the red are the gas molecules, and the blue are also gas molecules. So it's diffusion in gases. Whereas on this side, I want you to see another kind of diffusion. Through the water. And so before, water was coming out of the sponge. But now, as you can see, water is coming out. It's not coming out, it's coming in. It's actually, water is getting attracted. So there's attraction. So this is also another kind of diffusion process. So here the water is diffusing into the sponge. So the point to make here is there are many different modes and mechanisms of this diffusion process. And so we need to know some of those and try to see how we can handle it in doing computation for some uh, real process. Okay, so what are my learning outcomes for this chapter? I want you to see that all kinds of mass transfer processes can be divided into random. Let me get my pointer here, pointer, laser. So all kinds of mass transfer processes can be divided into random or directed and their combinations. So we want to see examples of random and directed. Then we will get into a lot more detail in terms of the mechanisms of molecular diffusion of mass and how it depends on the concentration gradient. And then apply the laws of this mass flux in diffusion and diffusion-like processes. So for example, dispersion. It doesn't always have to be molecular diffusion. And then explain convective mass transfer. So if you recall, in heat transfer, we talked about conduction, convection, radiation. And we are saying mass transfer is analogous, except that we don't have radiation in mass transfer. Mass doesn't radiate. If mass is moving out, being thrown out, that we have to handle using laws of dynamics. So we don't think of as mass radiating. So then in case of mass, we have following heat transfer, we have a diffusion-like process, which is what we had for heat conduction. Instead, we have the mass diffusion here. And for convection, we had a convection equation, and here we'll have an almost pretty much identical equation for convection mass transfer from a surface. And so again, like I say all the time, that at the end of this chapter, you are going to have this formula and this formula. That's all we'll have. So why not we skip the chapter and I just give you the formula and just tell you what these symbols mean. Well, as we know that it doesn't work that way. To really be able to use these formulas intelligently and correctly, we need to know what goes into the formula, what's the basis, and have a much clearer understanding of what they really stand for. So, here the point is we are getting into diffusion, but we all have some idea of diffusion. It's not like we have never heard of diffusion and this is the only class. This guy in BE, that's me, is just telling you what diffusion. What is diffusion? You all have some idea. So let's try to bring that out. Let's try to sort of recap. Okay. So I ask you to stop the video now and try to answer this question, what we already know. So here we have oxygen transport through a contact lens. So outside there is more oxygen, and let me go back here. Outside there's more oxygen, inside there's less, and oxygen transports this way, And so I want you to contrast these two situations that are otherwise identical, but the contact lens here is thicker. So which one would have more oxygen transport and why? I need you to think of this in a you know, as specific, and maybe even try to get little quantitative, how the two situations will differ. So please stop the video and spend a maybe 3 minutes to 4 minutes thinking about this process before you go on. This really helps in kind of absorbing the material later. Okay, so now we get into introduction part of this chapter, and I want to show you examples of movement of mass, random and directed. So ready? We'll just show you examples, really just pictures and animations. So here, this is an example of molecular diffusion. So here, these molecules are moving randomly. It doesn't know where there is more or where there is less. It's not trying to go from where there is more to where there is less of red in a very intelligent way. It's just moving randomly. And the net effect of that is it is spreading out from where there is more to where there is less. So this is an example of molecular diffusion where the molecules are kind of moving around randomly. Here is a biological example. Let's see if I can get this going. Okay, yeah. So this Brownian motion, again, in this case, the microbes are going randomly, and they are moving around because of their own energy. That's all. Okay, and they are not moving towards food, or in this case they're moving pretty randomly. So this kind of motion, and this could be one of the Brownian motion, and these kinds of motions are also random movement. So let's look at more examples. So this capillary diffusion of water in the pores.
Touch it to the water. And so before, water was coming out of the sponge. But now, as you can see, water.
That reference to water coming out was when I had a wet sponge and squeezing. So you can ignore that comment. Now you see water
coming out. It's not coming out, it's coming in. It's actually water is getting attracted. So there's attraction between the sponge molecules and water, and it's pulling water into the sponge.
So here you see the water is being attracted or pulled up by capillarity. So if you think of capillary tubes, you probably know about this, that as you touch the capillary tube, then water is pulled up into the tube. But the point is, in this sponge, it is not, the pore spaces are not all identical. So the amount of lifting that the water is having, or how far the water moves, is not going to be same throughout. In fact, you can see a little bit of this. Let me put the point. You can see here that it's not like one perfect horizontal line. So there is some randomness in this movement. Let's look at another one. So as you can see that the smoke, as it's moving out from the stack, it's also spreading. You see the diameter here was just this little, and here it's much higher. So it's spreading out, and it's spreading out because of the surrounding air that is turbulent, and that is helping the smoke to spread out. So this is a dispersion process. It is not exactly, it's definitely not molecular diffusion, let's say, but it turns out the nature of these processes are kind of analogous, and we can uh, treat these random movements the same way. And now let's look at some directed movement separate from this kind of a random movement. So here you can see there is flow. So if there's flow, it's the pressure that is driving the flow. So the flow is definitely going in one direction. So this is an example of directed movement. Um, I'm sure you talk about this all the time in your fluids class. Um, in the same way, just like here you have pressure driven flow in a tube, you can think of a porous medium as like a bundle of tubes. So you have pressure driven flow in a porous media. This could be sand, this could be our body tissue, it could be bone. And so pressure drives flow through this. So of course, there is a direction. It's not going randomly. Um, Here is an example of directed movement from biology. So in this case, bacteria, as we'll see in a second, is attracted by this sugar crystal. And let me get rid of the pointer, I think. Yeah. And so now you can see. So here you at least see a directed component. So we can think of this kind of a directed motion can actually be described quantitatively. For example, the velocity is proportional to chemical gradient, meaning where it's trying to go where the chemical concentrations are higher. So here is another one that is electrically driven. So use of voltages. So you're now applying a voltage, and of course you can make things electrically move along the voltage, and so that's what you're seeing here. You see that? So you apply the voltage, and so the only point to make here is when you apply a voltage, current goes in one direction, or some mass movement would be following the voltage gradient. So it's a directed movement, not a random movement. And again, we can calculate the velocity of such directed movement from voltage gradient. We're not getting into the details of these formulas here. Okay, so all these different mechanisms for movement or transport will be folded into two modes. Look, we're going to go nuts if, you know, if we have so many different types of diffusion. And so this is not a biology class, or it's not even a physics class. We have to somehow do the engineering, meaning we have to get an idea how long does it take to diffuse. And so we should be able to treat these many different processes using because they are similar in their uh, construction, because they carry the same kind of random movement. I want to describe all of these so very different processes here. Let me All of these different processes, molecular diffusion, Brownian motion, capillary dispersion, by one formula, because they share the same kind of physics, even though they're in different contexts. So the actual numbers would be different, but they share. So that is the random type of movement. And then the other group is directed. One group is random, other group is directed. Directed can be pressure driven in a tube, pressure driven in a porous medium, electrically driven, or chemotactic. These are just four examples. There are many, many examples. The point in this group is it is not random movement, there is a flow. Uh, there's directionality. There is some flow direction that it has some sort of a velocity in a particular direction, as opposed to just diffusing, which is the other group, diffusing in all different ways. Okay, so now we get into the details of the modes of mass transfer. So as I said earlier, this chapter is about two uh, of these modes. Like we had conduction, convection. Here we have diffusion and convection. And so first, let's talk about diffusion. So molecular diffusion, as you can see, let me again. Okay. So this is my animation of molecular diffusion where the reds are diffusing into blue. So you can have other molecular diffusion. For example, here you put some solute. Let's say you put some salt or sugar molecules, then they get into the solution and then they diffuse into the solution. So you see the reds are diffusing into the blue. And if you give it long time, then this is going to be the final equilibrated solution. And you can see more animation of this kind of random movement. Okay, so you can see it's because the molecules have energy, they're just moving randomly, and so they're spreading out. Okay, and it's a slow process overall. Okay, so we have to put some, we have to put some formula to it. We have to be able to compute this quantitatively. We can't just keep describing these using nice figures or nice animations. So now diffusion is described by Fick's law, just like Fourier's law, as you will see in a second. So let's take the situation of a solid let's take a towel. Let's take a wood, let's say, or anything that has wet, that is more wet on one side and dry on the other side. So from the wet side, water will diffuse to the other side. And so in case of solid, this could be capillarity. But you can also think of the one that you saw, the molecular diffusion. You could think of, okay, so on this side, I have more vapor, and on this side, I have less vapor. So it's going from more, where there is more, to where there is less. So how do I describe this? So first of all, this we kind of know that it's going to go from where there is more to where there is less. And so if we think of a concentration profile, so C for concentration and A is A in this case, sorry, there are two different A's here. This A is for this cross-sectional area, and so here um, co the concentration of whatever stuff that is diffusing. So let's call that A. So the concentration has this kind of a profile. On this side is more and this side is less. So the mass flux along X, so JAX, J for mass flux, so it is just like Q double prime that we use for heat transfer. So in fact, it's exactly like that. And this A is what is the stuff that is moving through, and X is the direction. So this mass flux, how, at what rate stuff is moving is proportional to the concentration gradient. Because you can see that first of all, this is exact same as Fourier's law. And how we say it in Fourier's law is the rate at which things will go, how much heat will go through this will depend on how big a temperature difference we have between this end, x equal to 0, and the other end. So just like that here, how big a concentration difference do we have? That must determine, how fast things will go. But also, given the two concentration differences, if they're spread apart by a very large distance, then it's not going to go as fast. And that's the dx part. So it's really dCA dx, meaning the rate at which concentration is changing with x. So that is my concentration gradient. So rate of stuff flowing and the concentration gradient is the driving force. So this will give, let's say this is a solid and vapor is diffusing through this. So this is saying the rate at which vapor is diffusing through is proportional to vapor concentration gradient. dCA or dC vapor dx. But and I know, and everybody knows that the vapor isn't going to move the same way through all different materials. So there has to be some material uh, aspect that should come in. How fast does vapor move in this material? So that will come through the constant as we remove the proportionality. So mass flux is equal to minus DAB, or mass diffusivity. So what is AB? So A is the stuff that is moving, like I keep saying vapor, and B is the solid. So here if we say vapor is moving through the solid, and so DAB is mass diffusivity. So that brings in this proportionality constant, brings in, okay, what type of material is it? And what kind of a molecule is it going through? It's going to bring in both aspects. What type of material it's diffusing through and what is diffusing through. And so then this is mass flux. So it's kg per meter square per second. So you notice this is equivalent to heat flux, because heat flux was what? Watts per meter square, right? So we're going to see that in just a second. So mass flow is then mass flux times the area for flow. So in this case, if the mass is moving in this direction, the area over which the mass is moving is A. Unfortunately, it's the same symbol, but so mass flow is going to be mass flux, here JAX multiplied by this area A. Okay, so now let's look at this. Again, this is the same animation of mass diffusion in a gas, and I have the formulas from heat transfer that you have already done. So heat flux is equal to minus K del T del X, and mass flux, you notice, is kind of identical formula. So JAX, meaning kilogram of A per unit time moving per unit area, meter square. So kilogram per unit area per unit time is equal to minus some diffusivity times concentration gradient. So here heat flux is minus K thermal conductivity times temperature gradient. I'm hoping you would say that, well, that isn't exactly the same, because here it's mass diffusivity and here K has what units? It's watts per meter per degrees Kelvin. So it's not, it doesn't look like exactly the same, but it actually is. And so let's do this one extra step. So I can divide K by rho Cp and multiply by rho Cp, and then they're identical, literally. So what is K over rho Cp? It's thermal diffusivity. Its unit is meter square per second. It's exact same as this mass diffusivity in terms of the units and the analogy. They're two different things. Energy is moving, energy is where mass is moving, but they're analogous. And so just to make sure they're totally analogous, what is Ca? Is the amount that is there, amount of mass that is there. So it's kilograms per meter cube. When I divided and multiplied by rho CPT, you may recall MCPT is joules. So rho CPT is joules per meter cube, just like here kg per meter cube. So instead of mass per unit volume, we had energy per unit volume, or we had energy per unit volume and we have mass per unit volume. So it's completely analogous, and I want you to see that is the reason we have heat and mass transfer in the same class, That's really is the reason. And this analogy also moves into fluid, as you will see in Professor Rowe's class, and we'll even do a joint kind of a homework like thing that you'll see the fluid also has this analogy. But one reason to give you why fluids is a separate class, it'll be too much to do all three in the same class. Okay, so now again, I am asking you, and this time you need at least 5 minutes. Okay, so you need to pause the video now or after not right now. Let me describe the problem, and then you pause the video, and then you try to work on this little problem. And when the the talk ends, when the lecture ends, like in in class, at the end you submit some piece of work. So for this lecture, you submit the work that you do on this page, on this slide. Okay, so here again we have two identical situations, again with contact lens, but just for the sake of discussion, I have a contact lens with two sides are, it's a slab, okay, so it has no curvature, and you are given a diffusivity of oxygen in contact lens. So if we follow that AB that we just did in the previous slide here, AB, so here is oxygen and B is the contact lens, and your DAB is given here in meters square per second. And then this side B has the higher concentration of oxygen, so it's given in some mass amount per meter cube. On the left side, we have the lower concentration. So this side is air, this side is I, and we are given concentrations on both boundaries, and we're also given the distance. And I happen to think of x starting from here. And just to not make things complicated, you can use the same x direction. The figure on the right is identical in every way except two things. One is the contact lens is not a slab, so it has a curvature, so it's like a circular, so it's more closer to what you see in this picture here. And then the concentration profile here is not linear like the one on the left. Okay, so those two are the only differences. The concentration profile is different, and the lens has a curvature. So at this point, please pause the video and work on this, and this is what you submit as your work to Canvas. Now, to keep going, I just have a couple more slides. So we try to get some idea, some feel for what is this DAB, the diffusivity in meters square per second. So here, as you see, the reds are moving, diffusing into the blue. So my red is the A, and the blue are the B's. So DAB is diffusivity of red in blue. How do we try to really understand what this diffusivity really mean physically? So this diffusivity is a measure of how fast a group of molecules is moving. Okay, not one molecule, but averaged over a group. So then suppose we follow the movements of one molecule. Okay, so this time just one molecule. So it starts from here and then it moves at very high speed, but it goes and hits another molecule and then it gets bounced. So let me again get the pointer. So it goes from here, bounce to here. And then this time it got some empty path, so it could go quite a bit until it again hits another one, and then it gets bounced this way, and then hits another one, gets bounced this way, hits this one, comes this way, and then bounces there, and then again moves this way, bounced, and then after some time, t, let's say it's here. But suppose I am talking about only the movement in the x direction, you notice even though it moved so much, because it keeps bouncing and then moving randomly, the distance that it has moved from initial here to the final here is this distance, x. So the diffusivity is actually related to these distances moved. And this is exactly how diffusivity is defined. So if I take the movement x that this molecule has, okay, so only in the x direction, if I take the movement that this molecule has and I square it, okay, because it could have gone in the negative direction. So we don't want to cancel out those movement, but let's say I square it and I do this for a group of molecules and I average the x squared, the distance moved squared for this molecule is x squared, and then I have many others, x1 squared, x2 squared. And then I take the average of that divided by 2t, the time over which this x movement has happened. So again, to repeat, x is the distance moved by this one molecule. I take it and square it. Then I take movement of another molecule. I find the distance it has moved over the same time and square it. And I take the average of those x squared and then divide by 2t. That is really what the diffusivity means. So the primary thing I want you to see from here is I want you to always think of diffusivity as a measure of displacement. It's a measure of displacement. So it's measure of distance moved per unit time, meter squared per second. So square of the distance moved per unit time, but of course averaged over many. So if there is this kind of a distance concept that it has moved so much, and so I have a square of the distances and average together, then that, since that is square of the distance, if I take the square root, so that's like a distance. And so you can think of diffusion velocity as that distance divided by time. We don't need to get into these details, but here I just plugged in for x squared here from this equation. So I just plugged in 2 dt from this equation here, 2 dt raised to the power half and all that. So all this is saying that there you can think of some sort of a diffusional velocity as well. So by analogy, thermal, so here we just talked about diffusivity is measure of distance, some mass moved. By analogy, thermal diffusivity, which is also meter square per second, is a measure of how far thermal energy moves per unit time. You can think of how far the thermal front moves per unit time. Okay, so this diffusion velocity, even though we just talked about this diffusion velocity, it is much smaller than the molecular velocity. So if I go back to this picture, you see the molecular velocity starting from here, it's really fast. It's going a lot of distance, but effectively it's only going from here to here, okay? Because it keeps bouncing against other. Um, so let's go back here. So this diffusion velocity is much smaller than the molecular velocity. For example, if you consider, let's say, nitrogen gas at 1 atmosphere and about room temperature, the root mean square displacement, meaning that x distance, uh, square of it and averaged and then taken square root, square of it averaged over a number of molecules and then take the square root. So it moves only 0.0056, whereas the actual distance moved by the molecule is like 475 meters. So what we are saying is if we count all of these distances, that is what is meant by the 475 meters, but this x, the actual diffusive distance moved, is only 0.0056 meters. So diffusion is a very slow process, even when molecules are moving very fast because they're bouncing against each other. So to get an idea of this range of diffusivities, because gases are most mobile, they have the highest diffusivities. These look like small numbers, but for diffusivity, these are very high values. So diffusivities in gases are like 10 to the minus 5 or 10 to the minus 6 in meters square per second, because gases are most mobile, they can move most easily. Then diffusion in solid, it's like very difficult. Diffusion of solid in a solid is really difficult. So you see these are many orders of magnitude smaller. Liquid is in between. So if we put in, let's say, salt in water, so then we use these diffusivity in liquid, and that's in between. It's still much less mobile than the gases. So let's stop here for this one lecture because I will be away. I hope it will make some sense. I am sorry that I have to miss class going to this meeting for today, actually. Okay? No, it would be yesterday. Okay. See you Wednesday.